Good afternoon, students. Today we will start with the second chapter of our class 11 syllabus, that is atomic structure. Now first we will be dealing with the history of atomic theory. Now these days most people are somewhat aware of what an atom is and accept that they make up the things around us, right? Now for a long time the atomic structure was very much controversial, and to understand the chemistry is to understand the processes by which these particles and their components came to be an accepted knowledge. Now first, the atomic theory was given by whom? It was given by Democritus. Later, it was extended by John Dalton, right? Now, whatever was their theory, how they have proceeded with it, that you people have already learnt in your junior classes. Now, next, Thomson was the very person who has discovered electrons, and later he has given the model of an atom. So, third one was J.J. Thomson. Now, Thomson's atomic model was the famous plum pudding model. Now, what was stated in the model? Now, when he has given the model, as we have discussed few seconds back, that only electrons were discovered, protons were not discovered. So, his model very much looks like this. He said that an atom has a positively charged disk or a sphere at the center, and above that positively charged sphere, electrons were embedded. It was very much like we decorate cakes with some toppings, or we decorate a pudding with a plum. So this was the plum pudding model, right? So this disk was positively charged. Now we all know that this is not the actual structure of an atom. So what was the problem of this model was that the actual distribution of positively and negatively charged particles were not known, right? But the only advantage of the model was he stated that an atom is electrically neutral, right? Now after J.J. Thomson, next the model was given by Rutherford, right? So it was by Ernest Rutherford who has given the model. Now what Rutherford stated? He has first performed the famous gold foil experiment. Okay, so Ernest Rutherford, he has proceeded with the gold foil experiment. And from this experiment, we are not discussing about the experiment now. Now from this experiment he concluded that an atom has a positive charge at the very center. That means the positive charge is concentrated at the center of the atom. Okay, and that center was named as nucleus. So it was very much like this. At the center has a positive charge which is named as the nucleus, and the electrons are far away from the nucleus, making 99.95% of the empty space within the atom. So after the nucleus there's an empty space, and the empty space is large enough, so the positively charged center, the size of that is very small as compared to the size of the atom. So there are large empty spaces within the atom, and these are the electrons which revolve in these parts known as orbits. So this was the nucleus, right? But after Rutherford gave this model, Maxwell pointed out something. So what Maxwell said, that if an atom has a positively charged center with protons and negatively charged particles, that is electrons, are revolving around it, then how come atoms are stable? Why atoms are stable? Because if two oppositely charged bodies, they are in vicinity, maybe they are not very close, but they are in vicinity, so what will happen? One will be attracted towards the other. So an electron is attracted towards the nucleus. So the electron will not maintain that orbit. That means the electron is not going to maintain that specific path. And what happened continuously? It's going to emit energy in the form of electromagnetic radiations, and gradually it will come closer towards the nucleus, and a time will come when the electron is going to collide with the nucleus, and as a result the atom will collapse. So as he has stated something like this: if this is the positively charged center, electron is not maintaining this path, but rather following this spiral path, it will be accelerated towards the nucleus, and at last it will collide with it. Okay, so Maxwell was not wrong. So this was not the only problem. Later, other problems also came into existence apart from the stability concept, stability of an atom. What was that? The first thing which came into existence was, what about the emission spectra that we can see? So which are the problems? So the first one is stability of the atom. The next was, what about the emission spectra that we can see? So next problem was emission spectra. And what about the third problem? What it is about the different elements that make them emit different colors? So why different elements emit different colors? Right? So these were the problems. So Niels Bohr answered all these questions with his model of hydrogen atom. So the solution was given by Niels Bohr. So now we are going to learn about Bohr's model of hydrogen atom. So some postulates or points were specified by Bohr which overcame those drawbacks or those problems. And Bohr has also extended the idea of energy quantization, right? Now, what is energy quantization, or what is the concept of quantization, that we are going to see. Now, let us proceed with the important postulates which is given by Bohr. Now, what was the first postulate? The first postulate goes like this: electrons revolve around the nucleus in fixed circular paths. Okay, so here this is the important thing, fixed circular paths. And this was the very point which was a very first step to explain the stability of an atom, which was a major drawback in Rutherford's model, right? So what Bohr stated, that if we consider an atom like this, so if this is the nucleus, suppose this is the first shell, this is the second one, second orbit rather, this is the third one. Okay, now if it is the first shell, we are writing it n is equal to 1. N specifies the number of the shell, and later we will see the other significance of this term n. Then if it is the second shell, it is n equal to 2. If it is the third shell, it is n equal to 3. So Bohr said that electrons revolve around the nucleus in fixed circular paths. That means they are not going to emit radiations like this, and they will collide with the nucleus. So these fixed circular paths were termed as orbits or stationary states. Okay. And what is the meaning of this very term, stationary states? Stationary means one that is not going to change, right? So it means, stationary states means paths having constant energy and radius. Okay, so the radius of those paths or orbits were fixed and their energy is also fixed. So the electron is not going to follow a spiral path and collide with the nucleus. Okay, so that means, so again I am repeating, the above point eliminates an important drawback of Rutherford's model, right? Okay, so from here we can say that the atom is not going to collapse. Now, what about the second one, the second postulate? The second postulate states that the orbit of an electron does not change unless energy is absorbed or emitted. Okay, that means as long as an electron is revolving in a specific orbit, okay, it cannot change that orbit and move to some outer orbit or to some inner orbit. It cannot do so. It can only do so when we supply some energy to the electron or we extract away some energy from the electron. So until and unless we don't disturb the electron, we don't go for any kind of energy transaction, so the electron will maintain that path and it will continue to revolve in that path. Okay, so that means if energy is absorbed, so what will happen? Then an electron will jump from an inner shell to an outer shell. Okay. So if you are providing energy and if the electron is absorbing that energy, so its energy value will increase. So if its energy value will increase, it will not maintain that particular orbit, but it will go to an orbit having higher energy, provided that value of energy of the electron matches with that particular orbit. Okay, it's not that on absorbing energy it will go to an orbit, but its energy should match with that particular orbit, right? Now the next thing, if energy is released or energy is emitted, then what will happen? The electron will jump from outer shell to an inner shell, right? So from here we can say that if this is the nucleus and this is n equal to 1, the first orbit, this is n equal to 2, the second orbit, and this one n equal to 3, the third orbit, that means as we move away from the nucleus, then the energy value increases, right? This is the second one. So every path or orbit has different energy, and as we proceed outwards, energy increases, right? Now let us proceed with the third postulate. What is the third postulate? Now this third postulate deals with the second problem, that is, it tells us about the origin of atomic spectra. We have already seen that when an electron loses or emits energy, it jumps from a higher shell or a higher energy state to a lower shell or lower energy state. This loss of energy, means the difference, is manifested in terms of radiation. Okay. Now, what it states? Wavelength of radiation emitted by an atom depends upon the energy difference of initial and final states. Right. Got the point? So, what about the energy difference? The energy difference, suppose this is the first shell, this is the second shell, or the first one, this one is a lower energy shell, that this one is the higher energy. So, an electron is moving from this level to this level. Okay. Got the point? So, what is happening? What about the, how much, suppose that electron is absorbing energy, it is moving from one shell to the other shell, that means to a higher energy shell. Now, there the electron is not going to stay for a large interval. Why? Because that is not its own state. That means wherever the electron is, that is its ground state. That means its inherent position is its ground state. Now, whenever the electron is absorbing energy, it is moving to higher states. Now, it's not going to reside or stay in that higher state for a long interval. It's going to stay there for approximately 10 to the power minus 8 seconds, because that is its excited state. Then it's going to come back. When it will come back, what it will do, it will release that amount of energy which was absorbed. Okay. So, what is the difference? So, delta E, the energy difference, is equal to energy of the final state minus the energy of the initial state. Okay. So, again we know that this energy difference delta E is equal to h nu, which is equal to hc by lambda. Okay. So, whatever is the amount of energy that is reflected in the lambda value. So, here we can write that hc by lambda is equal to E final minus E initial. So, 1 by lambda is equal to 1 by hc, E final minus E initial. Okay. Now, let us see how emission spectra is explained by Bohr from this third postulate. Okay, so third postulate says that the energy difference delta E only gives the expression for wavelength. Okay, because delta E is equal to hc by lambda. Now, let us go for this thing, quantization, which gives rise to atomic spectra. Now, every orbit or every energy level or every state has a fixed value of energy for a particular species. Now, suppose we are writing like this: E1, energy of the first state; E2, energy of the second state or second orbit; E3, energy of the third state or third orbit; E4 for the fourth one. So, if you are writing E1, E2, E3, E4, so these are few fixed energy levels, right? Because their energies are fixed. So, as we are moving from an inner orbit to an outer orbit, what we are seeing? The energy increases. That we have seen, right? So, if each orbit or shell is having a particular value of energy, that means their energy values are fixed, then their difference is also fixed. So, if we go for the difference between E2 minus E1, which gives rise to delta E, or let us suppose the difference between the third and the second one, E3 minus E2, that is delta E. So, these also have some fixed values. If each state have fixed values, so their difference are also fixed values. And we already know that delta E is equal to hc by lambda. Okay. So, if delta E is fixed, lambda is also fixed. So, if lambda is having some fixed values, then we can say that the lambda values are quantized. So, if any quantity is allowed to take any fixed values, means they are not allowed to take any values they like, then that very thing is specified as quantized. Okay, that's why we can say, since lambda is allowed to have any fixed values, that's why in emission spectra we see only some fixed lines. Okay, we cannot see anything, any value or any broad region, but we see fixed lines. Okay, now the next one, the fourth postulate of Bohr says angular momentum of an electron is quantized. Right? Now, let us suppose this point specifies the nucleus. This is the orbit maintaining which the electron is revolving. Suppose, let's assume this as a circular path. If this is the electron and if this is the radius of the path, okay, and the mass of the electron is specified by m, and this is the velocity which is specified with its direction. So, what we are seeing, an electron is moving in a circular path with radius r, having mass m and velocity v. So, its angular momentum, which is denoted by L, we are taking the modulus of this. That means we are only concerned about its magnitude. So, that is equal to mvr. Right. Now, actually, you learn this in physics, that angular momentum is the cross product of radius and linear momentum. Okay. So, if it's a cross product, we know it is r into mv sine theta. Right. Now, here what is the angle between the radius and the velocity? It is 90 degree. Right. So, we can write this as r mv sine 90. So, it's 1. So, we are getting the angular momentum as mvr. So, we are not concerned about those things. That's not our context here. Okay. So, the magnitude of angular momentum is given by mvr. Now, what Bohr stated? Bohr stated that the angular momentum of an electron can have only some fixed values. The angular momentum of an electron can have only fixed values, which is given by this mathematical form, that mvr is equal to nh by 2 pi. Now, h is a constant, which is Planck's constant, 2 is a constant, pi is a constant. So, what about n? N here represents the number of the shell. So, if an electron is in the first shell, then its mvr is equal to 1 into h by 2 pi. If an electron is in the second shell, its mvr is equal to 2 into h by 2 pi. If it's in the third shell, mvr is equal to 3 into h by 2 pi. That means the angular momentum of an electron cannot take any value, but it must be an integral multiple of h by 2 pi. So, that means what? Angular momentum is not allowed to take any value. Again, I am repeating. It can only have some specific values. That means angular momentum is quantized. So, this is all about the postulates of Bohr. Now, in the next class, we are going to continue with the mathematical expressions for the energy, radius and velocity, and from there we will come into the concept of the wavelength emitted. What is the wavelength emitted? What is the magnitude of the wavelength when an electron goes for any transition, and what about the concept of Rydberg constant and all. Thank you.